Good afternoon, Dr. Ruchira. Good afternoon, Dr. Ruchira. Let's wait for 1 minute more.
Sure, Rohini. Thanks.
Okay, and now we have members joined. So until others join, let's start the session for today. So happy to see all of you joined, and it's with great pleasure that I welcome you all to this insightful webinar on thermal management of textile materials. And this is the first webinar of the Fiber Focus webinar series presented to you by the Division of Textile and Clothing Technology, ITUM, Institute of Technology, University of Moratuwa. ITUM recognizes the importance of collaboration and knowledge exchange in advancing the textile industry. By expanding ties with professionals, students, policymakers, researchers, and enthusiasts, ITUM aims to foster a vibrant ecosystem of innovation and learning. As a part of this commitment to knowledge dissemination, ITUM has launched the Fiber Focus webinar series. This initiative aims to provide a platform for discussing various aspects of textile and apparel industry, facilitating valuable insights and dialogue among the participants. The inaugural webinar features Dr. Ruchira Vijayasena, a senior lecturer at ITUM with over 10 years of extensive research experience in material development. Dr. Vijayasena is a prominent figure in the field, boasting numerous patents, commercialized products, and a rich portfolio of publications in material science and nanotechnology. His expertise and contribution are further underscored by his prior role as a senior scientist, research scientist in the prestigious institute, Sri Lanka Institute of Nanotechnology. In this webinar, Dr. Ruchira Vijayasena will share valuable insights on thermal management of textile materials, drawing his wealth of experience and expertise in the field. As we embark of the journey of exploration, I encourage each of you to actively participate, engage, and absorb the valuable insights that Dr. Ruchira has to offer. Whether you are a seasoned professional or a curious enthusiast, there's bound to be something profound to take away for today's session. Without further ado, I invite Dr. Ruchira to take the virtual stage and enlighten us with his wisdom and on thermal management of textile materials. So let's give a warm virtual welcome to our distinguished speaker. Thank you, and over to you, Dr. Ruchira.
Hey, thank you very much, Rohini. I mean, thank you very much, especially taking a time off to really start this session. And of course, thank you all for joining us. As Rohini said, this is the first webinar that Institute of Technology, University of Moratuwa has organized in its program. This is called Fiber Focus. So we are trying to make a community around our organization. We are primarily, if you take Institute of Technology, University of Moratuwa, Textile and Clothing Division, one of the leading institutes, especially catering for the skill enhancement of students who are we are particularly focused on the Sri Lankan textile and garment industry. And we thought it's also important that we enhance our sphere of influence, especially how we can, and especially in the ways that we can connect with the the industry, and especially the students from various other institutes, and similarly some and academics, how we can make this sort of a vibrant forum. And this is the first initiative, and we want to sort of try to enhance this. Not only webinars will be, there are certain other actions that are also planned. But today, it's going to be on our webinar is going to be on a very, very interesting topic. And I'm sure most of you, some of you, maybe from the industry, you may already know how important, how much of a keyword thermal management became in very recent years. Now, thermal management of textiles is what I've been, I mean, if you look at the research arena, after wearables, the topics around thermal management is one of the hottest in the current research field. So, as you know, the current research will be, I mean, so most of this work will come to the industry and see commercialization within 4 to 5 years time. And I'm pretty sure that it's going to be a very hot area in future to come. So today what we are trying to do is to take a what you call I mean, so this is 1 hour, approximately 1 hour lecture, and followed by a Q&A session. What we are trying to do is we will try to understand some of the basics of thermal management, especially relevant to textile materials. And I will also discuss about some of the applications, some of the approaches scientists and engineers and material developers have taken. And we'll be talking about some of the conventional approaches and some of the novel approaches, and also approaches that we see right now, particularly in the research, very, very advanced. And so we'll try to get we'll try to make a discussion around that. Yeah, so I have a little presentation I would like to share with you just to aid my delivery. Yeah, so this is our topic today. It's going to be on, okay, this, yeah. Perfect. All right. So this is going to be our topic today: advanced thermal management in textiles. So this is okay. My Ravin gave an introduction. I'm attached to this beautiful institute, Institute of Technology, University of Moratuwa. We invite you to come and visit us one day. I mean, it's a beautiful institute. It's located at Homagama, the top facility over here, and we have dedicated program for textiles and apparel. And yearly, we produce around 60 students for the industry, and we are affiliated to University of Morocco. And however, in my career, I've been I'm an active researcher. I've been before I start my career at ITUM, I was a senior research scientist at Sri Lanka Institute of Nanotech. I worked there for like 10 years, and in this discussion, I would like to bring some of the maybe bring a little bit of my exposure, some of the insights I had during that time, and try to relate some of these topics. So this is what I'm going to talk about, and I'm going to talk about human body as a thermal system, because when we talk about thermal management, we need to talk about a thermal system, because it doesn't make any sense. Any form of thermal management would not make any sense without understanding properly what's the thermal system that we are dealing with, and what are the perks, what are the parameters, the important aspect of that thermal system would really dictate how we have to work with the thermal management of textiles. So I think it's very important. And I'm going to discuss about 2 dimensions of textile heat management. Now, previously, like, a few years, I mean, conventionally, if you take textile thermal management, we looked at it from a very specific point of view. Now, over time, with the current literature, current work, current research, we can see there's another dimension of thermal management is emerging. And what is that? And we're going to talk about that. And we'll talk about conventional approaches, talk about advanced approaches, what we have right now, what we can see in the industry, and also we'll talk about some of the novel approaches. What are the advanced methodologies that people use, especially in the research area, and how they work, and we'll try to get some taste of those as well. Okay, so let's start with from a very basic level. Human body as a thermal system. Since we are talking about textiles and especially apparels, our thermal system is the human body. And it turns out that, I mean, it's something that you may have heard, like human body comprises of almost 37 trillion cells. 37 trillion. I mean, just to put into perspective, if you take Milky Way galaxy, it contains around 400 billion stars. That's like, if you just compare it, like in every, if you take a human, in the human body would contain almost like 300 times more cells than the stars in the Milky Way galaxy. And I mean, it's beyond comprehension. The beauty is that each cell, as we know in the human body, it performs a specific task. To perform a specific task, you need to work. Work involves some energy. So you need to put in some energy to perform an activity. Okay, so there in our body, there are so many different diverse set of cells, and each of them are built to perform a specific task, which requires that if you really look at it, a cell can be looked in the point of a small engine. Why? Because as engines require, now if you take an internal combustion engine, it requires some amount of so don't worry about recording. So I see some of the requests to record this. Don't worry, I'll be recording this, and I'll be uploading to a content sharing platform. And everybody who have registered for this newsletter, I'll be sharing it. So you will have the access to this content anytime. Okay, for all the people who have registered, I will share in the recording. Yeah, so back to the content. Now, if you take every cell can be looked as a small engine. And while internal combustion engine would oxidize or burn fuels or petroleum fuels, our cells would burn, oxidize, what we call oxidize glucose, sugars, maybe protein, fats, and things like that. And that's how we generate energy. Every cell generates energy. And so this, the thermodynamics dictate that if you burn energy to perform useful task, thermodynamics dictate that certain amount of heat will be dissipated. Okay, so there will be heat that is generated as a byproduct of this. There's no way that we can't eliminate heat production. Now, if you take an engine burns fuel and produce useful work. As a byproduct, there will be heat, and there will be a certain efficiency, therefore, for an engine. Similarly, if you take that very similar point of view, if you take that sort of point of view to look at cells, they are also the same. Therefore, so this is how we look at our body in the thermal perspective. So we have to look at it from the point of view that each of these cells generate certain amount of heat as a byproduct of their function. And now with that, we come to the first very important definition of when it's come to thermal management, especially relevant to textile systems, what we call metabolic rate. So metabolic rate is very important that we need to understand. Metabolic rate is simply is how much of energy a particular cell, I mean, not a cell, the body produce when it's at rest. It's a mm, indication of the amount of cellular oxidation. So what are the fuels that the cells take? Carbohydrate, fats, proteins, and things like that. And so the amount of, now this is what it is, the amount of energy that a typical body generate through oxidation of uh, uh, the fuels is what we call metabolic rate. And so this, as I previously told you, metabolic rate, the amount of heat generated, will be given for two different tasks. First, to perform useful functions like life-sustaining functions. There are so many functions that are going inside our body. And also there will be some amount of heat that is produced as a byproduct. Now, when
Hello.
it's in typical,
Hello. Okay.
yeah. So in
So,
typical,
appendix again. Uh, oh.
yeah, I'm sorry about that. Rovini, would you like to moderate, please? We are available.
Yeah, could please everyone keep your microphones on mute?
Yeah.
Dr. Ruchira, could you please
Yeah,
give me the host power so that I can check if
yeah, thank
somebody
you.
is not on.
Thank you.
Sorry, Ruchira. Thank you.
Yeah, yeah, all right. So let me, then, oh, you have to give me the sharing rights then. Rohini, I lost the sharing rights, sorry.
Yes, Dr. Ruchira, let me.
Yeah. Sorry about that, guys.
Okay, I shared the hosting power. Sorry, share.
Yeah.
Now you can share, Dr. Ruchira.
Thank you, thank you.
Okay.
Okay, so that's what I mean. So this is the first important definition that we need to be very, very, very thorough. Now, the amount of heat produced when a human body is at rest is around 85, or that we need to know this value. It's very important. It's approximately, it's about, it's close to the energy that is produced by a like 100 watt light bulb, the filament. So that much of energy is being produced inside the human body. This is at rest. However, when it's come to when a human body engages in active work, active physical activities, this amount of heat produced can significantly increase, especially in very strenuous exercises. The amount of body heat generation, this is not the useful work, this is the amount of body heat production, can even exceed 1,000 watts. Now, if you take that to the perspective, if you take a heater of 1,000 watt heater, imagine that you put this heater inside your body. That much of heat being generated. And so this is the golden rule of the thermal management. If unless our body can dissipate this amount of heat that is generated, we will run into very uncomfortable situations very soon. And even even if this is not managed, the heat stroke will set in, and if that is also ignored, then unfortunately death can also ensue. So that's how important this is. So our idea of thermal management, especially from a textile point of view, then has to be has to be around this concept, how we dissipate the amount of heat produced to the environment efficiently as possible, especially during when a person engage in physical activities. Because especially at rest, most of the textiles are capable to do that, but especially during exercise, when the amount of heat is this much high, how we manage this, so that ultimately the development, material development ultimately will boil down to this particular point. It's very well, like it's like a typical, if you take medium, like like walk like situation, not that heavy physical engagement would generate around 300 watts. That's the amount of energy that's being produced. And of course, a human body has so many different mechanisms that are built in to really manage this. So I mean, there are various mechanisms in place. Now, if you really look at human body, there are various ways our body can dissipate heat. Now, we are familiar with these two terms from our previous, So we are familiar with these two terms from our previous presentation. This is metabolic rate, and this is the amount of work done. And this is actually the heat produced. When it's come to physical activities, the amount of heat generation can be dissipated to the environment through main three methods. We have what you call radiative heat loss that is happening. That is the dissipation of the heat as radiation, black body radiation. And the convective heat loss, the air molecules will come and hit the thermal body, and it will take certain amount of heat energy when it's moving. So this is called the convective loss. That is one of the forms of heat loss. And of course, then we have the human body is available to generate sweat. And sweat mainly consists of moisture, and the moisture, when it evaporates, it takes an endotherm. That means it takes up energy, so that energy could be taken up by the body itself. Therefore, it's a mechanism of cooling. So these three are the main the modes of heat losses. So these are the modes of heat production, and these are the modes of heat losses. And so this is a very important equation. Yeah, this tells you how we balance the whole how we maintain, how we manage the thermal requirements, especially if we take the context of textiles. If the heat produced could be meshed, if we cannot mesh the heat produced with heat losses, what will happen is you have a positive gain of the heat. Okay, so that means the temperature of our body will rise. Temperature of the body will rise, and especially if the core body temperature increases at a certain point, it would be really problematic. So and also if we lose heat more than what we produce, that is also problematic. Our core body temperature will go down, because we know temperature is an indication of the amount of heat stored. Temperature is how much heat that we have in the thermal system. So therefore, so maintaining these two at a level, the ideal scenario is that the amount of heat produced should be equal to the heat loss, so that you have very in thermally, if you take a very smooth scenario, it's very easy to manage. Okay, then also something beyond this equation, there can also be heat gains. For instance, if you go outside, especially hot sunny day, your textile may absorb radiation coming from the sun. The temperature will go up, and also some of that heat will be absorbed by your body. That is a heat gain. Then there has to be some other parameter that has to be added to this. Okay, that is a sort of a gain that's another parameter. So these three, so the gains, production, and the losses, it what really truly balances this whole equation. And it's our goal as a material designer, material developer, to really understand the dynamics of these components and manage them so that we get the gains and the productions is equal to the losses. And this is the golden the requirement of the thermal management. Therefore, we call this the first dimension of the thermal management. This is the most conventional form of the conventional framework to look at the thermal management, especially in apparel and garment textile systems. Some of the other important figures now. So how much of energy being dissipated in each of these modes? Now, this is important. Yeah. Now, we might not take this for granted, but it apparently, so around 60% at rest, this is at rest. Apparently, around 60% of our body heat loss is actually due to what you call, black body radiation. So our body, as you know, it's higher than the temperature of the ambient. Therefore, so some of the laws predict that there will be a energy as radiation, there will be energy loss. And around 22%, around 20-25% of the heat loss is particularly to the evaporation. This is at rest, yeah. And of course, then we have 15% and also through conduction, small amount of heat being lost. Okay, so this is how usually the body loss is at rest. This is without any garments or anything like that. When you have garment on top, the things changes. But generally need to understand the radiation. It's a key element in this whole equation to balance this, because radiation, the radiation loss is very significant. Now, typically, so the radiation loss is given by what you call, it's actually a phenomena. As you know, any hot object would generate electromagnetic radiation, heat waves, infrared waves. Our body would generate heat waves or the electromagnetic radiation centered around 10 micrometer. It's like a very broad distribution around 10 micrometers. So this is a lot of heat that has been generated. Okay. So it's also important to understand this is at rest. When the human body engages in physical activity, the whole equation will change. So in that case, around 60% of the loss, will actually come from the evaporation, and around like 20-25% of the loss will actually come from the radiation. Yeah, so the basically these two inverted. So this is at rest, radiation 60%, evaporation around 20. When the human body engages in physical activity, these two reverses. It's also important to understand this. So that's to be understood. This is called the first dimension of the thermal management. Then when we introduce textiles, the thermal body that we are talking about, we have the second dimension of thermal management. We call this thermal comfort. Thermal comfort. Now, thermal comfort means how much satisfied you are with the thermal environment that you experience with the clothes on. Okay, so this is not strictly a physical phenomena. There are also some of the physical elements that attach to this, but also it can be psychological as well. Because why psychological? Because now, as you clearly know, I mean, when our body undergoes sudden temperature changes, heat changes, one of the ways that we try to thermoregulate is like sweating. There are various functions that get activated. Similarly, there's a psychological response also being activated that you feel a little bit uncomfortable. Why? Because the brain tells you to, that makes chemical that make you uncomfortable, because that's naturally then you are compelled to sort of leave that sort of environment. That's like a protective mechanism built in. And the concept of thermal comfort, we take this parameter as a key thing. Okay, so this is the second dimension. So the first dimension, if you, as conventionally they believe, if you tend to take the first dimension, if you fulfill the first dimension of thermal comfort, you'll be all right. No, that's not the case. There has to be some other elements that you need to really balance. So what are those elements? Now, the thermal comfort, so not only the previous one, like we talked about the heat production and heat losses, but there are certain other thermal characteristics related to what we call microclimate also coming. Now, what is a microclimate? Every time we have our free body and every time we put a textile or a barrier in front of the human body, we have a special area that is being developed, a space that is being developed in between these two, the fabric and the skin. And in that thermal space, you have different parameters compared to the ambient environment. And the material, the way it interacts with the skin also differs. So those thermal attributes now here determines what you call the thermal comfort. Now, for an example, heat absorption. How well your textile is able to absorb and conduct heat is something would really determine the thermal comfort that you experience. Yeah, heat and mass transfer from the outside. Now, outside and inside. So, if now, for an example, how well your garment or the textile can really manage sweat, how well it can pull the moisture from the inside to the outer side so that the evaporative cooling can take place. It's a very important aspect that determines the thermal comfort and also physical contact. And in certain materials, due to their inherent thermal conductivities, might trigger various different responses to our nervous system. So all these things can be taken in the thermal comfort. So this is the second dimension of thermal management that we have to consider. First dimension purely look at the amount of heat production, heat gain, and heat losses. This is also very important when we design materials. The secondly, we also need to look at the thermal parameters of the microclimate to really design a better textile material to manage it well. So this is second dimension. So that is that's what we need to first highlight. Okay, so this is the first part of our presentation. Now let's look at how people try to manage, manage the thermal attributes of textile materials. Let's first take some of the conventional approaches. Now, conventionally, how people approach this is particularly through identify climates. So we look at various, climatic attributes like humidity and average temperature, wind speed, things like that. And you divide various regions according to those attributes. You classify. And for those regions, you develop garments, especially, this is something that we also do. It's been continued. But this is the most conventional approach. So therefore, we can mainly, if you look at these categories, we can identify by analyzing various climatic conditions that are available in the world, we can basically identify 5 climatic conditions. We have polar climates, continental climates, temperate, tropical, and dry climates. So we approach these different climates separately. Now, if you take continental and polar climates, these are characterized by low average temperatures. That means if you take Stefan Boltzmann law, that's the law that dictates the amount of radiative heat loss, you can see excessive heat loss through radiation will occur, especially in these climates, because you can clearly see the TC, ambient temperature is low compared to your core body temperature, that's around 37. Now here it can be minus Celsius 10, like that. So excessive, the big difference. So this will increase the amount of radiative heat loss. If you take, these are some of the examples. If you take in if you analyze the amount of heat dissipated, you can clearly see, depending on the clothes the person wears, very high amount of heat is emitted, especially in the areas that are not covered, and also from the core part of your body. Okay, you can attempt to, the more you cover your body in these areas, this condition would help you to manage your, the storage heat. So what will happen in these type of scenarios? These are characterized by very high radiative heat loss, and convective heat loss is also high given the person is engaged in that type of activities, and also so these two tend to be very high. Therefore, they are very high. Therefore, the storage of heat will reduce very dramatically. So what we need to do is we try to. So most of the strategies are centered around preventing this heat loss, and you know what it is. Especially how when we design this type of especially the what you call the winter wear are designed. The radiative and convective heat loss, the transmission, and as well as the heat radiation, radiator losses are minimum. So bulky, thicker materials. So this is the most conventional approach. Yeah. And when we have tropical climates that are characterized by an average temperatures of 10 degrees to 30 degrees, we have moderate sort of both radiative, convective, and evaporative losses. And the major parameter that tend to govern or really, affect significantly is the evaporative heat loss in these type of areas. So the clothes that the textile that we select are actually centered around allowing evaporative heat loss. The cottons that allows absorb moisture and transport moisture, spread moisture so that the evaporation can take place. Of course, new materials have come in now. So like that. So we have open areas, lot of open areas like. So this is the tropical climate. This is how we, and when it's come to dry climates, so these these areas are characterized by heat gain, because the outside environment can be, the temperature can be higher than your core body temperature, or very close. It's very easy to gain the heat. If there's sun, if you're wearing a cloth, then you have to, there'll be a heat gain, positive heat gain. So you can clearly see, so this is again is characterized by high convection and evaporative losses, heat losses. And therefore, what we do is we try to sort of increase the evaporative heat loss. So we sometimes even go, we reduce the amount of textile we use so that the evaporation can be more. So we have the bare skin. So even higher. So these are these are what is called very conventional strategies. These are still being used, and we built on top of them. But you can clearly see, if you really look at the various garments that we design for various seasons, some of the elements are still preserved. Okay, winter wear has a very characteristic or a similar sort of pattern, and also the summer wear has very similar pattern. So that is preserved state. Okay, so this is called what we call conventional approach, where we look at very broadly what are the climatic conditions, and we try to build average materials. That's very important. Average materials that can perform in these type of conditions. However, these are currently being used, but when it's come to now, after some time, there have been a requirement for very niche sort of applications. Then very niche applications, especially for certain sportwear, in certain workwear that requires special situations. You cannot suppose an instant that a person needs to work in a dry condition, but still in dry climate, but still you won't be able to open up the board, open certain parts of your body for safety reasons, some things like and yeah, like that. So that's where the advanced concepts come in. Now, so one of the earliest advanced concepts that came into the world, especially in this area, is what you call how we enhance it's centered around how we enhance the operative fluid, especially in the context of tropical climates, and also for active wear. So one of the things that people initially looked at, it's the way how we can increase the evaporative heat loss. So in these cases, we look at those specific areas and we try to improve from the textile material point of view. Now, some of you may have heard this very popular product is called Coolmax. Now, Coolmax is a special type of a fiber. It has a very special cross section. So the cross section, unlike now, you usually have circular cross section, yeah. But in a Coolmax yarn, you have a very special cross section, so that will increase what you call capillaries. So now, what is a capillary? Capillary is that now suppose you have 3 threads in contact, 3 fibers in contact. When you have 3 fibers in contact, you have this space where some small space between these fibers are made. This is called a capillary. And capillary, as you know, it's like a pump. If you put a capillary tube to water, you can see a rise in liquid. That means that it's able to perform work. Now, so in Coolmax textile material, what you do is you increase the area. You make the fiber cross section in such a way that capillaries, the amount of capillaries number of capillaries can be enhanced, and they can be smaller so that the liquid height can be high. That is one of the approaches. And also this very popular approach is called thermal regulation. These are some of the advanced approaches. Now here they use wax material, wax. So as you know, wax are very interesting, wax materials, because they, in room temperature, in typical room temperature, somewhere let's say around 30 degrees, they remain as solids. However, if temperature increases, they can become liquids. So from solid to liquid phase transfer, during that process, it absorbs what you call latent heat. Latent heat is very significant, tend to be very high. I mean, if you take the amount of heat that is required for 1 kilogram of wax to go from one phase to another, is very significant. So what you do is you put a little bit these particles in a thread. So this becomes as a thermal buffer. So remember, we told, I initially told the one of the key elements of thermal comfort is what we call the thermal conduction, then thermal the capacity of the textile material. So you increase that capacity, then there's no sudden shocks because it can regulate by because some of these wax particle can become liquids, absorb heat, and it can regulate this. So sudden changes due to temperature changes or body activities, heat generations would be regulated into much more smoother sort of conditions. So this is one of the aspects. And so these are some of the products that are already available. And also this is also interesting. Now you can see the various way various approaches people have taken. Now there's also this product called OmniHeat. It's a type of material we use. Now the previous ones are, now the Coolmax is centered in evaporative. And the wax particle, this one, the OmniHeat is centered around what you call the thermal conduction and thermal regulation. Now, OmniHeat is, they produce a reflective coating at the inside of the textile. It's a metallic coating. So that, as we all know, metals tend to reflect electromagnetic radiation. So the amount of the black body radiation human body produces, it will reflect back to the body. So there's less chance for the radiative heat, especially for winter wear. People can, this has been used. So especially in winter wear, to reduce the radiative loss, you incorporate this type of reflective materials in the inner side of the fabric, so the heat will be reflected back. So so effectively you reduce the heat losses. So also one of you can see different approaches, and also another approach that's already in the market. It's called AeroReact. So it's a special type of a fiber. The fiber has a special property. It changes its, it tends to shrink depending on either moisture or temperature. So when it shrinks, you can see that the dimensions of the textile material, the knitted material, woven material will change. And it will open up more areas for the thermal evaporation to take place. It's much efficient, therefore, than with one of the, especially if you take the summer climates, one of the key modes of thermal regulation is through the evaporative. So this, like a smart system, it regulates the openings of the textile structure so that you have, depending on the temperature that person feels and the conditions, the evaporative losses can be mediated or regulated. This is sort of a smart sort of an application. As you can see, different ways now people are looking at targeting individual components of the heat loss. I mean, of course, we can't do much about the heat production because then that has to, that works with the human body itself. So we can't do much about that. But what we do is we work with the other ways of heat losses, and we try to regulate them. And this is also very interesting. It's a product that was introduced by one of the sport brands. This incorporates a sugar molecule. This molecule is called xylitol. Xylitol is very interesting because upon moisture absorption, it undergoes endothermic response. That means that xylitol that xylitol solution, when you add xylitol to water, the whole thing becomes cooler. Like when if you can remember from your from good old days back at university doing chemistry experiments, if you put ammonia to water, the whole thing becomes cooler. Similarly, xylitol is a solid. When moisture touches xylitol, it becomes cooler. So you feel much more. So obviously, your body in temperature increases when you work out. Sweat produced. That sweat will activate xylitol, produce an endotherm that will cool your body back again. So these are the various material approaches you can take. Yeah, see, this is also interesting. So here, this is beyond this equation. So It's not to do with any of these things, but you incorporate a negative component, heat component through introduction of silent. So this is different approaches. And also it's also possible to enhance, to play with the equation by what we call by working with the conductivity of the textile materials, because it so if you can how fast your textile material can conduct the heat from inner side to outer side will determine how faster the convective action will take place. Yeah, faster it can transmit, the body cools down faster, because otherwise textile is just a buffer. There tend to be some sort of a difference in the transmission. We don't want that. So textiles are being produced to really increase the textile, the thermal conductivity. So these are some of the approaches that people have taken. And so these are what we call the advanced approaches. Let us look at some of the approaches that are out there in the research domain. And you might experience some of these things coming to the market in coming years. So so these are some of the pillars. If you look at, a lot of work has been dedicated, a lot of people are investigating these type of materials. But if you really look at most of these works, we would be able to categorize them into 4 different pillars. What are those pillars? We have passive radiation control. I will talk about these things: active responsive structures, conductive structures, and active woolworm structure. Let me delve into each of these in coming slide. Now, one of the very interesting technologies came up very recently is this one. So here what we do is, now a conventional material, if you really look at, now we discuss the thermal, what you call radiative heat loss is very important aspect in a human heat loss. Now, typical materials, if you take cotton, nylon, polyester, things like that, they tend to absorb heat that is dissipated by human bodies. Okay, so the heat energy, the dissipation I discussed previously also, will primarily occur around in infrared region. So typical materials have higher absorption in this area. Higher absorption. So this is the absorption. Higher absorption in this area. And obviously in visible range also, visible range, that is the human eye sensitive range, they have higher absorption, because it obviously has to be, otherwise a material become a see-through material, they lose the purpose. But what we really want a material to be opaque, especially in the visible dimension, visible aspect, visible range of the electromagnetic radiation. Okay, so but conventional materials, the problem with the conventional material is that many of the conventional material, if you take, they are opaque in both visible as well as infrared regions. Now, lot of work recently have been dedicated to developing textile materials that are only opaque in the visible range, but transparent in the infrared range. See, so you can see the transmission is high, the absorbance is high in the visible range. See, and the absorbance is low, almost zero. Absorbance is how much of energy it's been absorbed in particular wavelength. In a particular wavelength, you can see almost zero in infrared. So they appear as a normal textile material, but it can effectively, like when it's come to radiative heat loss, it is as if there's no textile. It completely transmit the transmission is almost 100%. The heat loss is so if you wear this type of material, it's like not wearing any garments at all from a thermal perspective. Yeah, you can clearly see the normal textile, human body radiation won't be able to transmit. Visible light will also be not be able to transmit. It's important. Air convection is also there. And people, what researchers, what they try to do is they try to develop textile materials that have higher, so they are able to, these materials are able to transmit black body radiation. They will also reflect human light, so it will be opaque so that there's no see-through effect, and air convection is also possible. And these are some of the materials. A lot of work now I've seen recently, like this area like exploded like last 2 years. A lot of work has been done. Yeah, this is called passive radiation control. This is just a material thing. So you reflect visible light, but you transmit the infrared portion. So I think this will come to the market very soon. So they have developed. You can clearly see it's reflect the solar spectrum, but it is almost transparent when it's come to the mid-infrared region. It's very, very important. But a typical textile material is like very constant in both visible as well as infrared. It's very, very important. Yeah. And a lot of work has been dedicated to making textile materials that have what you call passive conductive structure. So that we incorporate special nanomaterials or micromaterials that are aligned so that the transformation, the transmission of heat is very, very efficient. So heat transfer become very, very efficient in this. So typical textile materials have polymers. The polymers are randomly oriented. So therefore, especially when it's come to heat transmission, there can be limitations. But what you do is, especially when it's come to, you develop these special structures because they have, and they make it in a certain way that there's a orientation of the materials that really helps you in terms of thermal transmission. A lot of work has been, especially composites related work. You can clearly see, even if you take the cross section, you can clearly see special morphology that they take. And there are also a lot of work that has been dedicated for making active cooling garments. So these materials really, if you supply a little bit of energy, they cool down themselves. Like the Pelletier coolers we have, only the flexible versions. Lot of similar products that came to the, especially we can see a lot of work, especially in the research area, we see this. Yeah, so these are also being done. And also materials that are responsive. Now this one, this particular product, it's a product in the sense like it's a material research, published research work. This thread consists of a yarn or fiber that can absorb body radiation, and depending on that amount of heat that is generated, and open up. So when you open up, you increase the bulkiness of the material so that thermal conduction can be, the insulative property can be regulated appropriately. And these are some of the approaches that we take. So the special way that, especially used in nanotechnology, these are being produced. Yeah. And also some of the other work that incorporates is one of the work that I've been involved into. So incorporation of nanomaterials or micromaterials that can actively generate heat on the textile material itself. So especially like winter like situation. So whatever the solar radiation that is present, the visible light, it will convert to active heat, generate heat in those areas. And it will, you can clearly see, you take a control sample and a treated sample, you expose it to sunlight or the visible light, you can see the temperature increases. So actively generate. So one of the work that I involved in. and you can use it for even moisture evaporation as well. Okay, so like that. So these were some of the things that I wanted to highlight during this lecture. So with that, we come to the conclusion of the delivery, but I would like to take some of the I hope you were able to get some insights out of it. Thank you very much for your patience and and because you were present in this session. Thank you. If you have some questions, I would like to sort of try and answer.
Thank you, Dr. Ruchira.
Yeah.
If the participants are having any questions, now it's time to ask.
So you can, if you want, you can send it as a chat also. You can also connect with me.
Hi, sir.
Yeah, hi.
This is Anupama.
Hi.
Yeah, thank you very much for this. It's really valuable, and we got a lot of information with that. Now, my question is, I saw many materials can control the heat from the level which is now from the level with the fabric which is in the original, and then it's increase the heat or decrease back to the original level. I don't know what you get what I mean. It's like now say fabric can be absorb the heat and also come back to the original position where it was at originally. My question is, are there any material which feel cool, go beyond the level which is in the original form and also absorb the heat more than what had with the original, like a battery, and retain the heat and release it whenever required, and also it's like active kind of battery. When feel cold, it release the energy. When it's warm, it absorb the heat from the body and keep it, retain it inside the material, and when required, it's releasing. Is it possible, like kind of
Yeah, so
battery type of thing?
yeah, that's very possible. If you take, there are two ways that you can approach this. The first one, I mean, there is some work that is relevant to this as well. If you take phase change materials, is one of the, I think, the most commonly used. Now, if you take wax particle, suppose a wax particle that goes through phase transformation at 34 degrees. So at lower than 34 degrees, it remains as a solid. And higher than 34 degrees, it becomes a liquid. And during the transformation, it absorbs a lot of heat. Okay, it absorbs a lot of heat. Now, suppose the temperature now if the climate comes to a temperature of like 36, it absorbs a lot of heat and it snows. Now, suppose the temperature goes down. So you entered the room or you entered some other environment that the temperature is low. Then what will happen is that wax particle, the liquid wax, will come back to the solid wax. During that process, a lot of heat will be dissipated, dissipated back to the body. So that is one of the ways. So the what you call phase change materials have a that sort of a property. And also there are some other materials, especially salts, some of them are iron salts. So, I mean, there are salts that when they get hydrated, when they get dissolved in water, they generate exotherm or endotherm. So, like, for an example, xylitol is like that. So, they are not responsive to the temperature, but they're responsive to liquid or similar stimuli. So that can also generate heat or absorb. So these two are the most, sort of conventional, approaches that are taken. Like they are like small batteries of heat, small banks of heat that dissipate or absorb according to the depending on the external stimulus. So I think these are the ones that we have right.
Okay, are these in the markets as in the mass production right now?
So I think the what you call the phase change materials are already here, but the only thing is that current limitation of the phase change materials is that the quantity of phase change material that you can incorporate in a textile material is so low that the thermoregulation activity, that buffering strength is low, the amount of heat that can regulate. So that is the limitation. Now, a lot of work, especially in the research fund, being dedicated to now developing materials that have higher thermal capacities, so that they be able to generate and absorb heat. I mean, the quantity is large. So they have been worked, but I'm not sure the ones that we see in the market are currently mainly on wax based that they have moderate thermal capacities.
Okay, thank you very much, sir.
Yeah. We have
Dr.
another.
Ruchira, yes,
Yeah.
there's another question shared in the chat.
Yeah.
Tasindu is asking for the active, cool, or warm structure. Would we select the correct polymer, or is it there any other aspects we should consider?
Yeah. So the active cool warm structures, it's the at least the one I showed you. So it produces it's a what you call an electronic structure. So we have a junction. So what you use is you use two different types of materials and you make a electric junction between these two. So the material has to be very specific. So the junction is such that when you apply a bias voltage, one side will be cooler and the other side will be hotter. So these are called actually the Peltier or so we call this Peltier. So we have to use those specific textile materials which has that particular property. Only then it will work. So these are currently mainly in the research domain. So you have another question? Yeah. What is the reason?
There's another question, Dr. Ruchira. What
Yeah.
is the reason of this research boost in this area?
Yeah, especially now, especially if you take thermal management textiles, we've been looking at it from a very conventional point of view. But as you know, textile industry is now catering to very specific, very niche sort of applications. A lot of, it's been very competitive. There's a lot of players and people want to find their own niches. And one of the ways to cater those specific needs is through technology. And that's why the typical, the very like overarching blanket solutions are no longer, although they have been used for certain application, may not be sufficient. So that's why a lot of people are going into that. And also, especially the material development capabilities enhanced, especially with the invent of nanotechnology and nano-related, our ability to manipulate these materials at very minute scale, and that enhance our material, engineering capability. So that also, I think, contributed for this effect.
Thank you, Dr. Ruchira. For now, we don't have any other questions in the chat. If the
I
participants
have
yes.
small question.
Yes.
Yeah.
Thank you very much, Dr. Ruchira, sharing this all information and really valuable. I just wanted to ask about the natural substrates wise, if we looking at the thermal regulation or kind of a way of thermal resistance, how well this can be incorporated, the polymer or is blending yarn with the natural, or is there any natural component that can get incorporated for the natural levels in textile?
If you really look at most of the natural materials, if you take, if you take cotton, wool, these things, wool is very well known for its low thermal conductivity. Is because of the nature of the fiber is such that it tends to make a lot of porous areas. And when you have a lot of air gaps, it reduces the thermal conductivity. And cotton has the cotton has a very special property. It has moderate thermal conductivity, very pliable and preferable moisture absorbance level. So that being used for tropical climate, especially warm and summer related climates. Uh, then, uh, so then there have been development, especially on top of these natural materials, new developments have been made. Especially if you take this particular instance. Now, this material. So yeah, not this. So I have seen multiple applications where they've been trying to change the existing natural materials by modifying them with some other materials like nanomaterials. They incorporate that nanomaterial have very specific properties, thermal properties. That helps in terms of the that helps to give that a very niche sort of to cater thermal requirements. So that I have, but if you take most of these new and advanced applications are centered around synthetic materials because it's easier to modify them and make composites out of them. Yeah. So I didn't know
Thank you.
Yeah.
Yeah, thank you. Just a follow-up question on the same, like most of natural materials, as you said, the wool and others are really going to the bit of a thicker material level. So,
Yeah.
and even the cotton that you can make air porosity increasing and make it somewhat thermal resistant.
Yeah.
So, but in some industry now, moving more thinner and lighter weight fabric, but gives the performance of thermal retention or controlling. So this is where I finding some challenges. So that's the reason I pointed whether any applications were there to build that thermal ability.
Yeah, so that's interesting. So especially with a specific sort of a thing, I would like to delve into this in separate forum. Maybe, yeah, so we can, so we need to understand what is the requirement properly, and probably based on that, we be able to find a suitable approach.
Right, thank you.
Yeah, so we have to take it separately. But there are, if you look at, I mean, there have been, but I should tell you, most of the work that we see, especially in the research arena, is primarily centered around synthetic materials. I've seen some research that they use synthetic material, but augmented with some other special material that has special properties.
Thank you very much.
Dr. Ruchira, we are having another question in the chat.
Yeah.
If there is any air layer or any cellular structure in between the fabric, how that will affect for the thermal transmission rate? Is there any way to optimize that?
Yes, any cellular layer, air, especially air or a vacuum cavity, would really reduce the thermal transmission. Because if you take the thermal conductivity of air is much lower compared to any solid materials. It's something to do with the density. In air, we have a very low density compared to solid materials. So that means the density simply means how closer the atoms, and when the atoms are closer, the thermal conductivity is you get a higher thermal conductivity. So when you have what will happen is, especially you have, depending on the distribution of these cavities in a composite material, the heat tends to transmit in certain pathways. It will try to find a pathway that is optimal for the thermal transmission to occur. However, because of these cavities, they they will become, uh, they, I mean, so they will develop a resistance, and overall thermal transmission will drop significantly. And especially, I mean, if you can make these cavities even smaller into the nano cavities level, some other thermal phenomena will kick in. Especially if we take like aerogel materials. Aerogel materials have very small cavities, very small. So the even phonon, so the heat cannot really penetrate any. So heat get blocked completely. So depending on the pore size and the pore geometry, so special effects can also be taken place. So thermal transmission, so just to summarize, thermal transmission rate will significantly reduce depending on the if there's a cellular structure, cavity or pore structure in the material, and also the geometry, distribution, and the size of the pore has very special effect, and especially at small pores, the transmission rate can be exponentially reduced in certain cases. If you take aerogels, very low, the lowest thermal conductivity is known to man are produced with introducing pores to these structures.
Do we have any other questions?
One more thing, sir. What are the pros or the no, not the pros and cons or any barrier having with this nano channel and this micropores or anything related to the maybe the diability or else yarn count to the fabric, strength or anything? Any barriers there?
Yes. Now, okay. So when you make something smaller, let's say you take a fiber, you make it smaller. When you make it smaller, what will happen is the surface area will tend to increase. And when the surface area tend to increase, then you must do a lot of work to send the surface area so the interaction volume, so the interaction space, what you call the area, like even if you take dyeing or any other chemical treatment, then now you have to deal with very high surface area. Now, in these type of systems, if, for instance, now if you try to dye these type of systems, let's say you try to dye a nanofiber, and it's very when you have high surface area, the dye uptake is very fast. Very surface area is very high, so uptake is very high. But when it's come to the fastness properties, the reverse will also occur, because when you have high surface area, you have very high diffusion coming. So it can work in both ways. There are especially when it's come to processing, some of the processings can be, I mean, this is not only limited to dyeing, for many properties. Sometimes it's easy to incorporate or introduce other special properties to this material, but they are what you call their durability has been somewhat of a problem in the long, because of the very high surface area that we need to build. That's one of the things. And also one of the other problems, especially from the mechanical point of view, is that when you make something smaller, you tend to increase the defects rate. I mean, if you take a chain, the strength of a chain is determined by its weakest point. Similarly, I mean, other chain links can be very strong, but if you have a weak chain, that's what the tensile strength of a chain. Similarly, when you try to manipulate these materials at very small scale, if you introduce more defects, then the thermal properties, mechanical properties tend to degrade very rapidly. So you see this I mean, especially nano and microfibers, you can see when it's come to peeling and all, it's very difficult. The micropart plastic generation, all that's very high. Why? Mechanically, the degradation is very high. So like that, yes. So it can work in both ways. Now, generally, two things that we need to be very careful when you make things small, when you try to manipulate things at a smaller level, you introduce very large amount of surface area. That is one of the things. Secondly, you tend to introduce more defects, so that the control has to be very precise in these materials. Yeah.
So I have one question. Can I ask?
Yeah.
So when we consider thermal regulations, what are the is there any specific testing protocol or any what are the testings we have in when we consider thermal regulations?
Yeah. So as I told you, I mean, thermal regulation. If you take the conventional at the first dimension, the thermal, uh, thermal comfort would centered around radiative losses, convective losses, and evaporative losses. So there are many tests that can tell you individually about each of these effects. Now, for an example, if you take the wicking test, I mean, this is generally taken as the telltale test for wicking materials. Why? So the evaporative, like the high performance wicking materials, because if a material wicks, that means its ability to get the moisture from inside of the fabric to the outside. So the evaporation is so making the evaporation much more efficient. So it's the wicking test is general test. So it tells you about the evaporative heat loss. And you can, now for an example, the convective heat loss, you can look at the thermal conductivities, spreading, the moisture transfer rate, like how fast you can transmit moisture from one side to other. This test is called a moisture pickup test. Those tests are there. And especially you can, so when it's come to radiative heat loss, you can look at the transmission, the electromagnetic transmission, the reflectance, absorbance of the electromagnetic radiation at different wavelengths. All these tests are there. But none of these are actually, I wouldn't say, I mean, some of these are called standard tests. But many of these tests would really fall under what you call characterizations. Now, there's not standard test for to evaluate the electromagnetic absorption, light absorption, textile materials. But we have cover factor analysis, but the what you call when you look at electromagnetic absorption, that's a characterization that will come under characterization. Yeah. So these are there are so many tests like that. So what most of these tests and characterization would be centered around these three: radiative heat loss, convective, and evaporative heat loss. So you can design so many tests. Now I've seen hundreds of different tests. But if you want to take like like indicative measurement of thermal moisture management, there's something called moisture management test, MMT. That tells you it measures a special equipment that measures multiple parameters, including thermal conductivity, moisture wicking rate, moisture spreading rate, and few other. I can't now remember. So they gives an index, MMT, moisture management. So that's been popular, somewhat popular, especially in these domains.
Thank you, sir. Clear.
Yeah.
Any other questions from the audience?
Yeah, so I will take this only one. So we'll take this as the final question. Okay, if we are going to incorporate certain nanoparticles into fabrics, at what stage those should be added into the industrial piecework? You can introduce nanoparticles at primarily at 4 different stages. You can add them during, especially if you take synthetics, the fiber spinning stage. You add it to the polymer, so you spin, you get the fibers incorporated in nanoparticles. Then you can also add it in at the stage of dyeing. You can dyeing. So when you dye, try to send nanoparticles into the structure. That's also one of the things that you can do. And also finishing stage. So what you call, so pad dry cure, like, you send it across some a solution that contain nanoparticles, you perform curing. That is also, and also printing. So these are what the commonly used techniques, especially to introduce nanoparticles to textile materials. Yeah, okay. So with that, now we shall conclude. Okay, so thank you. I hope you enjoyed the session. And there will be another session which is planned, especially on the characterization, especially how we can use what you call electron microscope for textile specific analysis. What are the ways that we can use them? So this is going to be, I think, the next webinar. After like 2 weeks time, we'll announce this. Thank you very much for your presence in this webinar. Thank you very much. You can always connect with me through LinkedIn. And also, it would be a great help for us to, if you can share this message with your colleagues so that we have a larger community so that we can collaboratively, especially industry and academia can really work hand in hand, especially trying to develop this sector. Yeah, thank you very much. Thank you very much.
Thank you very much,
Thank
Dr.
you.
Ruchija.
Thank you, sir.
Thank you.
Thank you, Mr. Roni.
Yes. Good.